The supercell foundation, tornadoes rarely come from ordinary thunderstorms. Instead, they usually form within supercells, enormous rotating storms that can last for hours. A supercell is defined by its mesocyclone, a deep, spinning updraft that drives the storm's power. These giants feed on warm, moist air at the surface and release enormous amounts of energy high into the atmosphere. Without this organized structure, tornadoes are much less likely. The RFD is born inside this complex machine, and understanding supercells is the first step to understanding how RFDs fuel tornadoes. Defining the RFD, the rear flank downdraft, or RFD, is a mass of sinking air that develops on the backside of a supercell thunderstorm. It descends rapidly from the mid-levels of the storm and then curves around the rotating updraft. Visually, it can create a clear slot, a dramatic bright gap near the storm's base that storm chasers often recognize as a sign that a tornado may form. The RFD is not just an afterthought. It's often the deciding factor between a storm producing nothing more than rain and hail, or spawning a violent tornado. The science of RFD formation. So, how does this descending air current form? As rain and hail fall through the storm, they begin to evaporate in the dry air aloft. Evaporation cools the air, making it denser. This heavier air then sinks quickly, pulled downward by gravity. At the same time, pressure differences inside the rotating mesocyclone create pathways for the air to accelerate. When it reaches the ground, it spreads outward in powerful gusts, wrapping around the storm like an invisible hand. RFD and tornado birth. The RFD plays two key roles in tornado formation. First, as it wraps around the mesocyclone, it tightens the rotation, much like a skater pulling their arms inward to spin faster. Second, it brings cooler air into contact with the storm's warm inflow. This sharp temperature contrast intensifies the updraft and stretches the rotation downward. Together, these processes can pull the spinning air column toward the ground, allowing a tornado funnel to form. In many cases, tornadoes touch down right where the RFD and inflow collide. Too cold versus just right. Not every RFD leads to a tornado. If the descending air is too cold and dense, it can choke off the storm's warm inflow. Think of it like pouring water on fire. The storm loses fuel, and the tornado dies before forming. On the other hand, if the RFD is only slightly cooler than the inflow, it creates the perfect balance. The updraft remains strong, the rotation tightens, and a tornado often follows. This delicate Goldilocks zone is one of the reasons forecasting tornadoes remains so challenging. Storm chasers and RFD clues. For storm chasers, spotting an RFD is a thrilling and dangerous moment. They look for the clear slot carving into the storm's base, sudden blasts of wind rushing out, or a sharp drop in temperature. Some describe the experience as the storm taking a deep breath before unleashing a tornado. These signs can appear only minutes before touchdown, making the RFD one of the best real-time clues of tornado formation. However, being inside an RFD can also be hazardous, as winds can exceed hurricane strength and carry hail and debris. Radar and meteorologist tools. On radar, the RFD can sometimes be identified as a hook echo, a curved appendage on the storm's reflectivity image, where precipitation has been wrapped around the mesocyclone. Dual polarization radar can also pick up on differences in precipitation size and type within the RFD. Meteorologists use these signatures, along with reports from spotters and chasers, to decide when to issue tornado warnings. The presence of a strong RFD often tips the scale from possible to likely in forecasting. Historical tornado cases and RFDs. Many of history's strongest tornadoes have shown clear RFD involvement. In the 1999 Bridge Creekmore F5 tornado in Oklahoma, scientists noted a powerful, warm RFD wrapping tightly into the mesocyclone just before the tornado's violent intensification. In the 2011 Joplin EF5 tornado, survivors recalled blasts of wind from the RFD moments before the funnel descended. These examples demonstrate that RFDs aren't just abstract science. They are real-world signals that often precede devastation. RFD as tornado killer. Sometimes the RFD plays the opposite role, shutting a storm down. If the downdraft air crashes into the surface with too much force and spreads too far, it can overwhelm the storm's inflow. The updraft collapses, and the storm gusts out. Chasers often see this as the storm producing a powerful burst of wind and rain, but then rapidly losing its organized structure. In these situations, the RFD prevents a tornado rather than fueling one. The RFD in human experience. For people on the ground, the RFD can be their first real warning. A sudden blast of cool wind, a shift in direction, or a burst of rain and debris may signal that a tornado is imminent. Unlike radar or meteorological terms, these are physical sensations that anyone can recognize. In fact, many tornado survivors describe a sharp, rushing wind and eerie calm immediately afterward, classic signatures of the RFD passing through. The RFD's role in forecasting and warnings. Because tornadoes can form in minutes, forecasters need every tool possible to anticipate them. The RFD has become a crucial part of this toolbox. By analyzing radar scans, surface data, and chaser reports, meteorologists can gauge whether an RFD is favorable or unfavorable for tornadoes. This helps determine whether to issue a warning and how urgent that warning should be. In tornado-prone regions, even a few extra minutes of warning time can save countless lives. Scientific mystery of the RFD. Despite decades of study, scientists still don't fully understand the RFD. Why do some produce weak EF0 tornadoes while others unleash EF5 monsters? What exact mix of temperature, moisture, and wind speed creates the perfect RFD? Projects like Vortex 2 have gathered mountains of data, but the complexity of storms means every case is slightly different. The RFD remains one of the biggest mysteries in tornado science, and unlocking it could revolutionize forecasting. The RFD in public safety, beyond science. The RFD has real implications for safety. Communities in Tornado Alley, the Midwest, and the South rely on accurate forecasts. Understanding the RFD helps forecasters improve warning accuracy, which means more families reach shelter in time. Schools, hospitals, and emergency managers all benefit when meteorologists understand the RFD's role. In short, studying the RFD isn't just academic, it's about protecting lives. The RFD is the hidden engine. Finally, it's important to recognize that the RFD is not just a side effect. It's often the hidden engine of tornado formation. Without it, many storms would remain rotating but harmless. With it, the delicate balance of rising and sinking air transforms into a spinning column of destruction. The RFD reminds us that tornadoes are not random. They are the result of complex interactions, and even a subtle shift in air temperature or direction can decide whether a storm fizzles or becomes catastrophic. The rear flank downdraft is one of the most fascinating and important features in tornado science. Born from sinking cool air inside supercells, the RFD can either fuel a tornado or shut it down entirely. Its balance of temperature and moisture determines whether the storm will unleash destruction or collapse into rain and wind. For storm chasers, it's the clear slot and gusty winds that signal danger. For meteorologists, it's a radar clue that can guide life-saving warnings. And for communities, it's a reminder that understanding the hidden forces inside storms is the key to survival. The tornado funnel may grab our attention, but behind the scenes, the RFD is the silent architect. It is the invisible force that often decides the outcome of nature's most violent storms.